G'day chemistry students. In this video we're looking at dot point 5.3.1. This is our first lesson where we're going to start looking at equilibrium from a much more quantitative standpoint. And the aim of this lesson is to learn some new rules and strategies around how we actually write equations for equilibrium so that we can then go about doing some calculations and some quantitative comparison and all sorts of stuff. Let's get into it. So first off, what you're going to find in this topic is that we're going to start expressing concentration in a slightly different way, and that's this one down the bottom. Maybe you've seen something written down as like concentration of or C of like this, but what you will see quite commonly is that concentrations of substances get expressed using square brackets. And so we'll have a square bracket on the outside, the chemical formula, and then a closing of that square bracket. And that's mostly used for the reason of convenience. It can get quite messy when you're writing lots of concentrations in an equation or in a single equation to have lots of little C's and then subscript and all that sort of stuff. Here we're highlighting the main thing that's important, which is the chemical species, and making sure that that's nice, big and bold, and then noting that we're working with concentrations with simple square brackets. In this situation, distinguishing between your chemical species is significantly more important, and hopefully you'll see that as we move through the rest of the lesson. We can also use this notation for gases. Gases have their own concentration, number of particles in a volume of a container. As long as your gases are in a closed container, they can have a concentration and can be expressed in exactly the same way. So that now moves us on to equilibrium expressions, and they're a way of writing up an equation to show what's happening in each specific kind of chemical system, every kind of equilibrium. So if there's a reaction that's in equilibrium, or there's a chemical system that's on its way to forming equilibrium, we're looking at reactions that are reversible, and both reactions are actively happening at the same time. So they'll have one of these double arrowed symbols to show that. And what we can do is represent each reaction using one of these equilibrium expressions. And we can use these expressions for lots of different reasons. We can look at the value of the expression when we substitute all the values in, and we can actually use that to describe whether or not the equilibrium is reactant favored or product favored, meaning is there a greater concentration of reactants and products or vice versa. We can also see if we have like a real chemical system that's in front of us, if we can measure all the concentrations inside that container. Is that system at equilibrium yet, or is it still approaching? We can also even predict the direction that the equilibrium still needs to shift towards. And also, if we know that the system is in equilibrium, we can also find the concentrations of unknown substances. So when expressing equilibrium mathematically, we write up one of these equilibrium expressions, and I've got a couple of general forms. The main idea is that we put the concentration of all of the products on the top of the fraction, that numerator, and the concentration of all of the reactants on the denominator of the fraction. So you'll always see a fraction, products on top, reactants on bottom. Now, that's a gross oversimplification of how these work, because what we need to do is not only just put all of the products on the top and all of the reactants on the bottom, but we need to multiply any concentrations of products and multiply any concentration of reactants. So a word that I might use quite frequently is product of products and product of reactants, meaning that we multiply the products together, we multiply the reactants together. The additional thing that we need to do as well is make sure that the coefficients that are on the outside here, so this might be a 1, a 2, a 3, a 4, for example, end up as indexes or exponents, powers that sit on top of each of the concentrations. So if little a was 1, little b was 2, little c was 3, little d was 4, this would be the concentration of chemical A to the power of 1, concentration of chemical B to the power of 2, concentration of the chemical C to the power of 3, concentration of chemical D to the power of 4. This formula might look a little bit confronting and a little bit weird to begin with, but it is a helpful aid once you understand how these equilibrium expressions sort of come about and are written up, which we'll get to shortly. What I also want to do in this lesson is compare two different values that use that equilibrium expression general formula, and that's KEQ and Q. We're going to talk about these two values in exceptionally more detail in future lessons. For now, what I want to talk about is that the value of KEQ represents concentrations of all of the substances when they're already in equilibrium, and that Q represents concentrations of substances in a system that can reach equilibrium but may not be there yet. And there's different uses for these. They kind of outline the uses that I talked about here in a little bit more detail. Again, we'll get back to those in future lessons, but I did just want to introduce that KEQ and Q value that we're going to be calculating in future activities. Something else that I want to emphasize is that when we're writing up equilibrium expressions, we can't put in substances that are a part of the reaction that are solids and liquids, because generally speaking, they don't have measurable concentrations in aqueous and gaseous systems. We're almost entirely going to be looking at gaseous and aqueous systems when we are doing our activities in this module. Technically, you can have concentrations of solids and liquids, but not in the same way, but not in examples that we sort of cover in this year 11 and 12 course. So if you see a solid or a liquid, it's usually a pretty safe assumption that they will not be included in the equilibrium expressions, and they just don't get written into that equation that you make at all. What we may also see is that we can change the stoichiometry or reverse reaction equations, and that will have an effect on the equilibrium expression. So I have a reaction here for hydrogen and oxygen gas forming water vapor, and the reverse reaction is also possible, water vapor forming oxygen and hydrogen gas. So I've used all of those general rules from this expression up here to write an equilibrium expression. So I've put all the reactants on the bottom, I've put the products on the top, and I've also looked at the coefficients on the hydrogen and the water and put them as indexes in the expression as well. You'll note that I've put multiplication down as just a little dot. So this is the concentration of O2 times the concentration of hydrogen to the power of 2. What I want to emphasize though really quickly is that if you were to flip the products and reactants around, the numerator and denominator has to flip as well. And that if you change the coefficients, so here I've kept the ratios the same, but I've divided the size or the value of the coefficients by 2 for all of these, then that also needs to be reflected in your indexes or exponents that you put on the top. So you'll notice that there is no coefficient on the hydrogen or the water, it's just a coefficient of 1, so I haven't put a power on either of those, and I've had to halve or put half for the coefficient for O2, so I had to put an index of half over here as well. Now I just want to go through a couple of quick examples and go through a few practice questions to sort of lead into the work that we'll be doing for our first lesson. So in this first question, we're simply being asked to write an equilibrium expression for the reaction between hydrogen gas, nitrogen gas, and its product, ammonia. So what I want to be mindful of first is that we want to be taking the product of all of the product concentrations on the numerator and the product of all of the reactant concentrations on the denominator. So for question 1, I'm just going to write out the expression and sort of talk you through how I would approach completing one of these problems. So I'm going to look at my products first. I've only got one, and that's the ammonia NH3, so I'm just going to write that down. And then underneath, I'm going to write down my reactant, so hydrogen gas, H2, and that's going to be multiplied. I'm just going to put a dot for multiplication. That's going to be multiplied by the concentration of the nitrogen gas, N2. Now, once I've got my products and reactants down and I've multiplied them all accordingly and the fraction's starting to take its form, the last thing that I need to do, and this is something that's quite easy to forget, but something that has to be done, is look at the coefficients that are present and make sure that the indexes go in the right spot. So 2 for ammonia and 3 for hydrogen. In the second question, we have an equilibrium between solid calcium chloride and the ions of calcium and chlorine. So for this expression, I need to write down my products first. So that's our calcium ions being multiplied by the concentration of the chloride ions. So they're in no problems. And then we would go and put in the reactants as well. But what we should notice is that the calcium chloride is solid. So it can't have a concentration within the container that that this solid is in. So what we'd be assuming for a reaction like this is that you'd have a container, maybe it's a beaker, there's water in it, and you've got your solid calcium chloride sitting at the bottom, and it's going out and forming ions in solution. Now that solid that's sitting at the bottom has no concentration like the ions do, so we don't put it in the equilibrium expression. In fact, what we've written so far as it stands is exactly what the equilibrium expression is. It's simply the concentration of calcium times the concentration of chlorine. So that form is already written out. The only thing that's missing that we need to add is the index there, because the chlorine and the calcium are in a 2-to-1 ratio. Now in this second question that I've got down the bottom, it's asking for a little bit more than what I'm actually going to do, because this is actually a calculation where we start calculating equilibrium constants, KEQs, stuff like that. But what I want to look at in particular is that there are two expressions here, or two equations here for the same reaction. And what you'll notice is that the coefficients on the outside are the things that are different. So I just wanted to quickly write both of those up and show that the equilibrium expression that we write is going to be different for both of those examples, despite the reaction being the same. So I'll quickly draw that up. So we've got H2 and I2 as our products. And then we've got hydrogen iodide as our reactant. And for this one, it's got a coefficient of 2. So I've put that in. Compare that to the other reaction though. Here we have our products again being H2 and I2. Our reactant is still hydrogen iodide, but the coefficients are different in this one. The hydrogen iodide has a coefficient of 1, so I write nothing down, and the hydrogen and the iodine have a coefficient of 0.5, so I put them down. Now, because these two expressions are different, what you will find is that if you were to substitute concentrations in, you would actually get different KEQ values. But that's a concept that we're going to explore in future lessons. Thank you very much, everyone. In the next lesson, what we're going to start doing are some calculations around this KEQ value and start to maybe make some predictions or use the values that we calculate to make some assumptions about the systems that we're looking at. But until next lesson, have a good one.